Hey, this is Physics 2211, Lab 4 Oscillations. Introduction. The purpose of the lab is to analyze the motion of a mass attached to a spring, moving in both oscillation and swinging motion. Use video analysis through Tracker to obtain position data in 2 dimensions, x and y. Build a computational model to predict the motion using physics principles. Compared observed motion with predicted motions. The assumptions are motion occurs in a 2D plane. The spring follows Hooke's law. Air resistance is negligible. Mass is treated as a point particle, and system experiences no significant energy loss. Important principles. Newton's second law is described as net force acting on an object equal to mass multiplied by its acceleration, and net force is equal to spring force plus the force of gravity. The equations are the force of the spring, force of gravity, kinetic energy, potential energy from gravity, potential energy from the spring, and the total energy, which is equal to 0. Procedures. Recorded a video of a mass attached to a spring undergoing oscillation and swinging motion. Ensured that the motion remained visible and within the plane of the camera. Imported the video into Tracker, tracked the position of mass frame by frame, extracted x and y position data, exported the file into a .csv file with x in column 1, y in column 2, and imported the data into a GlowScript computational model. Initial conditions. The variables where initial time, position, the mass, the relaxed length, the kinetic value of the spring, the initial velocity, and the position update and velocity update, and all of the energy change equations were inputted into GlowScript. The results preview with computational versus observed. The observed motion shows oscillation combined with swinging motion. The computational model predicts similar motion using physics equations. Both x and y directions show periodic behavior. Energy in the system remains approximately conserved. Small differences expected due to experimental limitations. Observed model. Motion tracked using video analysis. Observed behavior is oscillation along the spring direction and swinging motion in an arc. Motion is not purely vertical or horizontal, which is shown by the 2 graphs generated through the tracking model. GlowScript computational model, all of the code is inputted and changed according to the system, which generates the 2 images that are shown, one being the generation of the motion and the other one being the graph. The computational model analysis, model used GlowScript. Forces include spring force and gravitational force. Net force used to compute acceleration. Motion updated step by step using the velocity update and the position update. Model simulates both oscillation and swinging motion. The data comparison with the 2 graphs generated from the model versus the 2 graphs generated from Tracker. It compared an observed and predicted motion, agreement observed in both directions, and overall trajectory. Both showed oscillatory and periodic behavior, and the distances between the model and the data are small. Sources of error could have come from inaccurate point tracking and Tracker, calibration errors in video scaling, air resistance not included in the model, spring may not have behaved perfectly ideally, camera angle could have distorted it, and numerical approximation errors in simulation. Discussion and questions. Is the energy principle satisfied? Total energy remains approximately constant over time. Kinetic, gravitational, and spring potential energy continuously change. Energy shifts between forms, but total energy stays nearly constant. Small fluctuations are observed due to experimental and numerical error. This indicates that the energy principle is satisfied. Oscillation period comparison. In the x direction, a period for both directions is defined as time between peaks. Example of peak times that were found from the tracking model showed that the oscillatory period in the x direction is 2.37. Example peak times calculated from the tracking model for the y direction showed that the oscillation period was also calculated to be 2.37 seconds. Since the x direction and the y direction oscillation periods are approximate, motion is consistent in both directions. Equal periods indicate the motion is coupled in x and y directions. The system behaves as a single oscillating spring mass system in 2D. An agreement between periods supports the accuracy of the model. Small deviations are due to measurement uncertainty and tracking error. In conclusion, we successfully analyzed 2D spring mass motion using experimental and computational methods. Computational model accurately predicted observed motion. Energy in the system remained approximately conserved. Small differences explained by experimental and modeling limitations. And this demonstrates that complex motion can be described using fundamental physics principles.